Hello everyone, this is Eugene Licio, and today we're going to be discussing the physics of light and laser scanners. Just a note that this module will be pre-recorded. It will be broadcast on October 26th, 2018, but will be available for people to view in the future. This is module 2 of the IFSM Basic Laser Scanner Certification course. The previous module was on the history of laser scanning and of surveying as well. So today we're going to be talking about my favorite subject, which is the physics of light, something that I'm very interested in terms of operation and all the sort of underlying elements of how things work. This is going to be fairly basic, but we are going to be covering a number of different things. So the first thing we're going to be talking about, of course, is just light itself. We're going to move into the electromagnetic spectrum, talk about Lidar and lasers. We're going to talk about the types of laser scanners and how they operate. We're going to go into the basic components of the laser scanner and also talk about laser effects, things that we see that could go right or could go wrong, and then touch on the accuracy and error of laser scanners. Now, this is going to be sort of maintained to about 50 minutes or so, and as a result, we're not going to be able to cover every single thing under the sun, and certainly I don't think that I know everything under the sun. So this is a basic outline of the probably the most important topics on this subject. And of course, in the future, I'm hoping that we can improve on this and maybe add some additional information. And of course, the day of the certification, which is coming up actually in about a couple months, there's going to be a little bit more information presented, and we'll go into a little more detail. Okay, so let's move into it. Of course, at the very, very fundamental component of the laser scanner is light. And what is light? Well, I guess we have to think about that, and it's a very simple question, but in my research I found that it's a very, very difficult topic to discuss and sort of present to people. Many people say that light is just a form of electromagnetic radiation, but what does that mean actually? They say that it behaves like a particle and a wave, so it's kind of both. So the important thing to remember here is that it is in fact a wave, and we'll be discussing more about wavelengths, which makes up an important part of light in the different spectra. But part of the light, which is the electric part, is that it comes with a magnetic component as well. And in this little graphic you can see that the electrical part is going up and down, and the magnetic part, which is perpendicular to the electrical component, is at 90 degrees there. So it's a particle, it's also a wave. And probably the best way to communicate this is through a little video here. You can find this on YouTube, and it was part of a TED Talks, and it's really, really interesting. And this is what some researchers at MIT were able to do by using a sort of specially designed high-speed camera. And using multiple sensors, they're able to slow down and actually capture a photon of light. And so what I'll do is I'm just going to play this video here, and you'll see that there's a little bundle of light that enters this empty Coke bottle. You'll see that it goes through, it disperses, or you can just see the photon going there and going into the cap. Again, sort of explodes into colors there and even exits on the outside. Okay, until it sort of finally dissipates, just like that. So if you think about the light as a little packet that behaves like a wave and is also sort of like a particle, then that's really what light is. And of course, there are a lot of people still trying to provide very simple explanations for light. Not as easier said than done. But we can talk about what is unique about light. And there's a couple of things. Well, first one is the wavelength, as I mentioned before. So different types of light have different wavelengths, and that results in different types of spectra. Now, the wavelength is also related to the frequency, and that frequency is a measure of how many waves pass a specific point over a time interval. And normally we use the measure of hertz, which is how many waves pass a particular point in 1 second. So the first two components are wavelength, then the second one is frequency, and the third one is energy. So because light is a packet of energy, it has a wavelength, it has frequency, but it's also a certain amount of energy. And so shorter wavelengths require greater energy, or are packets of greater energy in themselves. And in this chart that I'm showing on the right here, what this is demonstrating is if you took for example, like an iron bar or metal bar, and you started to heat it, it would eventually start to glow. It would start to emit energy. It's absorbing, you're heating it, you're providing energy, and that energy needs to go someplace. So one of the ways that it can dissipate that energy is in the form of light, heat and light. And so light will change depending on the temperature. And you'll see here that if I look at the Celsius scale, and we're down very, very low at about 500 degrees Celsius, we're at a very faint red. Okay, we get into the blood red, and as we move towards hotter and hotter temperatures up to about 1205, we now start glowing or emitting light, which is very, very white. So the three components of light, again, are wavelength, frequency, and energy. And just to demonstrate that a little bit further here, there is a chart here on the visible spectra of light. And so you can see that we go from the violets on the left all the way up to the reds on the and dark reds on the right. And there's three charts that are associated with this scale. The first one is frequency, the second one is wavelength, and the third one is energy. Now, down here, energy is in electron volts, so when you're measuring very small energies, they'll use electron volts instead of joules. Wavelength is in nanometers, and frequency here is in terahertz. But nonetheless, what we have to look at here is that as we go to the left, you remember in the iron bar, we started with dark red, and then we started moving to brighter colors. So here the frequency is lower, and as we move to hotter, let's say, or brighter colors, okay, or towards the blue, we get higher frequencies. Okay. Now in terms of wavelength, it's the inverse. Okay, the wavelength gets smaller, and as you get into the lower energy, it gets longer. If we were to go from right to left, so let's say it was getting hotter, you can see down here in the energy that it goes from 1.6 to 3.1. So we're moving towards greater energy when we go to the left. Okay, so again, if we look back at this particular scale, we're moving from the dark, which is the cooler, to greater energy as we go to the brighter colors. Alright, so let's continue. Now what I'm showing you here is obviously just the visible spectra, but when we talk about the electromagnetic spectrum, we're actually talking about a very, very wide range of things here. So when we talk about the long and lower energy waves, we're talking about radio waves and microwaves. And then we move into infrared, visible, and you can see we're getting into higher energy and higher, smaller wavelengths on the right here, into the visible spectra, which we just looked at. Then we get into ultraviolet, X-ray, and then the very small high energy gamma rays. So the area that we're most interested in is right here. It's the infrared and the visible. The visible obviously because it affects us every day, and infrared also because that's where most of the laser scanners work, and that's the range between the visible and the infrared that much of the lasers that we deal with on a regular basis for range or where they're located. So in terms of the size of these wavelengths here, you can see at the infrared, we're talking about very, very small wavelengths, the size of a pinhead, and in the visible protozoans. And as we move towards microwaves and radio waves, we're getting much, much larger. As we go to the right here, as we go to X-rays and gamma rays, we're talking about very, very small wavelengths. Okay, let's move on. So this is another chart. In here, it's not just the visible spectra, but you can see we have ultraviolet radiation and we have infrared. Now here we've attached the scale of wavelengths in nanometers, and this is typically what we deal with when we're talking about laser scanners. So the range for laser scanners is usually in the near infrared, so here it says 800 to 1400, the IRA, and here, which is the 1400 to 3000 nanometer range, which is IRB. Okay, so in this particular range, okay, is where we'll find a lot of the laser scanners that we are working with. And actually, I'm going to point out here that around 1550, this is a very, very common wavelength that is used for laser scanners. And you'll see that it's just in the mid-infrared range over here. Now, and there are some here down just above the visible spectra that are at about 900. Some might be at around 800 here, but again, this is all non-visible. Now, a couple of unique things. You're going to hear me talk about certain wavelengths, and one of them is 1550. It's a very common wavelength that's used, okay, 1550 nanometers. And there's something unique about the infrared range that we don't see in the visible range. And so what I have here are two charts, and both of them related to how light is affected by moisture or by water absorption. And so if we look at the visible spectra here, okay, this little range down here, you'll see that the absorption of light is actually quite low. So in this range here, in the visible spectra, light will penetrate water. And so that's good for the fish, and that's good for people if we're underwater. We can see through the water for some distance, okay, so it doesn't get absorbed as well. But when we start moving into the near and into the mid ranges, and even the far, you'll see that we get this climbing scale here that goes up top, which means that the infrared range gets absorbed quite a bit when it comes to moisture. Now, let me point out, we talked about 1550 nanometers. So if this is 1000, this is micrometers, so it's 1000 nanometers. And if I move up this scale, so I've got 11, 12, 13, 14, 15, 50. So just in between these two bars, you'll see that as you go up, we've got like this peak here, this little spike that's here. Okay, so what this is telling me is that it gets absorbed by moisture quite a bit at this particular range here. We got this little spike. Now, let's move to the right here. There's another chart here, and this is a chart that discusses the absorption of certain spectra or light over different wavelengths. And here we're talking about micrometers, so we can convert that to nanometers just by multiplying by 1000. So 1550 nanometers would be right in this range. And now, instead of absorption, we're looking at how well these objects, okay, corn, tulip, poplar, soybean, will reflect. And you can see there's a graphic here, it says, or some text that says water absorption. So we get these dips here because at 1550 nanometers, and somewhere around here, around 2200 and maybe, I don't know, maybe 2500 or whatever that might be up here, we get absorption. So there's this little dip here, which means that you don't get as much energy reflected in that particular wavelength because it's getting absorbed by moisture. Hold that thought, because that is going to be coming up again. For the moment right now, let's talk about speed of light. How fast does light actually move? Well, one of the great things of light and why it gives us the ability to take so many measurements and at the speed at which we can is because of how fast it is, or what kind of speed that it runs at. So the speed of light you can find online is 299,792,458 meters per second. So if we do a little calculation using a speed equation, speed is equal to distance over time. And let's say we just take a value like 10 meters. How long does it take light, electromagnetic radiation, to travel 10 meters? Well, we can plug those numbers in and just isolate for time here and rearrange the equation. And when we do the numbers here, we have 3.335 to the negative 8 to the power of the negative 8 seconds. That is 33.35 nanoseconds, and I've written it out here at the bottom with all the zeros, and hopefully I wrote this correctly. But needless to say, there's a lot of zeros in front of these numbers here. So it's a very, very small amount of time. Now, this calculation is based on the speed of light in a vacuum or about air. Different media or different mediums have an effect on the speed of light. And so things that are denser than a vacuum or air or water or glass, they are all going to have a slight difference. And so here you'll see some notes that air is about only 0.03% more dense than a vacuum, and water about 25%, and glass about 35%. So it has an effect on the speed. It causes the light to slow down. Let's talk about Lidar and what Lidar means. Well, the concept of Lidar was originally published by an Irish physicist. His name was Edward Synge, and he had come up with the concept of Lidar before it was actually possible. And it really wasn't until about the 1960s, shortly after the invention of the laser, that Lidar was really put into action. And the idea here is that you're going to be emitting light or some type of wavelength of light, whether it be infrared or ultraviolet, and you're going to put some pulses or something towards an object, and you're basically going to capture the reflected signal, okay, by some kind of receiver, and you're able to tell something about that particular object, whether you're looking at distance or some other property it could be like for vegetation when you're doing aerial mapping or whatever it might be. But in our cases, we're really looking at the distance, so we're looking at range. So the term LiDAR itself was a combination of light and radar, so they just called it LiDAR. But today, it's come to be known as an acronym for Light Detection and Ranging. And originally, the very first use of LiDAR was to look at clouds or measure clouds, the height of the clouds. And I believe that I'd seen a reference to one of the Apollo missions using it to map the surface of the moon in 1971, which I thought was pretty cool. Now, typically, for lasers, we're talking about ultraviolet, visible, or near-infrared light. And those that part of the spectra is probably the most common for LiDAR to be used. Now, of course, LiDAR wouldn't be much without the laser, and so let's talk about lasers for just a second. In 1917, Albert Einstein was one of the first people to establish the foundation for the laser and how it might work. And at a conference in 1959, Gordon Gould published the term laser, and he actually defined it as light amplification by stimulated emission of radiation. So the first laser was built in 1960 by Theodore Maiman at Hughes Research Laboratories. And what's interesting is actually before the laser there was something called the maser, and it was the predecessor to the laser, but the M stood for microwave, so it was actually using a different part of the spectra, but it worked very similarly. But there were some challenges getting this to work with the laser, but of course that was solved later on. Now, there's two features of lasers that are very, very important and that make them somewhat unique. The first is that lasers have something called coherence, and the coherence is really about the fact that they can stay focused in a very narrow beam, just like a laser pointer. And this allows the energy to be focused over great distances. And you'll know, because if anybody's used a laser pointer, you'll know that you can point it, and it's not like a flashlight that just disperses light everywhere. It actually will focus this light on a very, very narrow beam and has very little divergence, when compared to regular light sources. The other thing that is very unique about lasers is that it has the ability to emit a very narrow or specific wavelength of light. And so this is often referred to as being monochromatic. Those two properties are very important for the laser, and it makes it unique when compared to other types of light. Okay, let's talk about the simple laser and how a simple laser might work. Now, this is not completely technically accurate. There are some exceptions, and there's a lot of little caveats here, but this is a good, I think, basic explanation of how a laser might work. So what we start with here is a chamber. So let's say that we have a cylinder here, okay, and inside this cylinder, we're going to have a mirror on one end, okay, a perfect mirror. And we're going to have a mirror on this other end. But on this particular mirror, we're going to have leave a small opening here. Or maybe if not an opening, we're going to have a part of this mirror that is somewhat transparent. It's not fully a mirror, okay? So there's a little escape hatch for things to escape on one side. And inside the chamber, we need to put something inside here that we can excite, or that we can provide energy to give off energy. So in some cases, they're using solid state devices. but of course gas or liquids are also very common. Okay, so it doesn't matter what's in here for the moment. Let's just assume that these are a whole bunch of different atoms that are sitting inside here. It's some material. And the first thing that we're going to do is we're going to apply energy to this somehow. And it could be other light sources, it could be something else, okay? But we're going to excite these atoms by giving them a heck of a lot of energy. Now, when you do that to an atom, the electrons will absorb energy, they jump to higher states, and then they jump to lower states. And when they do that, they give off other energy. So inside of this chamber, okay, you'll have these electrons that are jumping from different states, and they're giving off little photons of light inside here. Now these photons are sort of random. They're going all over the place in different directions. So not all of them bounce directly off the mirror. So some of them may reflect off here, and they come back this way and that way, and eventually they just sort of dissipate and diffuse. But there will be some that start to hit perpendicular here. And when they do that, they bounce back and forth between the mirrors. And what you end up with is a resonating wave, okay, like a standing wave that's in between these two particular mirrors. And once you have this particular condition, you have this little slot or this little opening that's here on the laser, and that allows a beam to exit out of the laser. So really what this is about adding energy to a bunch of atoms. You excite the electrons, they give off photons, these photons bounce around, and if you can sort of organize them in a way where you get a standing wave, then give them an escape hatch, they get out, and you get the laser portion that escapes on the right here. Now, there are a whole number and types of lasers for a number of different applications. So, there are lasers that cut metal, there are lasers that engrave, there's lasers that are used for surgery, so a whole number of different types and different forms, gas, liquid, solid state, you name it, over a very, very wide range here. So you'll see here in the infrared, the visible, and the ultraviolet, it covered a wide range. So just be aware that there are different colors and different strengths and different powers. Now, when it does come to power, safety is, of course, of importance here. And so we have to obviously be careful. Now, for the laser scanners, they are typically lower classes. Okay, so here, class 1 is inherently safe. It's contained in an enclosure, for example, in CD players. So if you do have a laser, it could be somewhat powerful, but if it's completely enclosed and there's no real risk of hitting you in the eye, then they'll classify it as a safer laser, let's say. And as you go up the list here, there are different types and different classes depending on whether or not it's visible light or infrared or invisible. But you see as you go up the list here, the conditions start to change. So class 2 is safe during normal use. Here what they're suggesting is that the blink reflex of the eye will prevent damage, and they usually contain this to about 1 milliwatt. Class 3R now gets up to about 5 milliwatts, so you have to be a little bit more careful here in terms of pointing things at people's eyes. And then class 3B can cause immediate eye damage. And when you start getting up to class 3B and class 4, these may typically end up being like scientific equipment and things, or maybe industrial equipment, things like that. So this is where you really have to be careful about having damage. Now, it's interesting that the laser scanner rotates around, as many of us know. So it isn't like for example, total station. A total station, for any of you who are familiar with it, you point at an object and then you fire a shot. And when it fires a shot, the total station isn't moving. It's actually taking a number of measurements with a still standing wave or just like a laser pointer would be pointing at an object. So in any condition, I think it's safe to say that we don't want to be staring at these units or trying to put yourself close and staring into the mirror or the components of any laser device. And I think that's just makes sense. It's just good practice. Having said that, there is some benefit. Remember, I was talking about the 1550 nanometer wavelength and how it gets absorbed by moisture. Well, what's interesting here is that infrared lasers with wavelengths longer than about 1.4 micrometers or 1400 nanometers are often referred to as eye safe because the cornea tends to absorb light at these wavelengths, protecting the retina from damage. So inherently, because of the chosen wavelength that we're talking about, we have some benefit in terms of eye safety because it doesn't penetrate as deep to the retina. The other thing that's useful about this particular wavelength is that the sun emits full spectra, a full spectrum of light, including 1550. But of course, 1550, because it gets absorbed by moisture, it also gets absorbed by moisture in the atmosphere. So when you consider a laser scanner that's on the ground, here, a terrestrial laser scanner, it isn't the same as looking at visible spectra, like, for example, on a sunny day. So if you were looking at just the visible light spectrum, it'd be very bright. So if you took a flashlight during the day and shined it on the ground, you'd be fighting with the sun. And so it's very difficult to distinguish that particular beam. But when you're looking just for the 1550 nanometer or very, very small wavelength of light, if most of it is absorbed by the atmosphere, then you don't get a lot of interference here, or you don't get a lot of noise from the sun at that particular wavelength. And that is another benefit of using the 1550 nanometer wavelength. So I put together just a very small table just of a few scanners and looking at the laser class and also the wavelength. And you'll see that all of them are class 1 laser. So all of them are classified as being safe. And I don't have a power rating for each of these, but I'm quite certain that the power is relatively low. But you'll see here that 1550 comes up in several cases here. So the 1550, one of them on the Regal, I wasn't sure what the wavelength was exactly, but it says near infrared, so it's probably, you know, up and around the same range. And you'll see that the Leica BLK here is down at about the 830 nanometer range, so it's a little bit lower, but nonetheless it's still a class 1 laser. Well, we've talked about lasers, classes, we've talked about the electromagnetic spectrum. What I'd like to do now is move into different types of lasers and how we calculate range or how we calculate distance. And so the first one that we're going to discuss, which I think is probably the easier of the two to understand, is time of flight. And some people refer to this as pulse-based. So I have a little video here, a little animation that I've created. So let's assume that we have a scanner. And the real difference here is that the scanner emits a pulse. We got this little laser pulse that goes out, it gets reflected off of a surface, and then it comes back. And you'll see at the top here that there is a timer, and that's really what we're doing. At the same time that you release that pulse, you start timing how long it takes for the round trip. In this case, we look at a simple speed equation. We want to calculate the distance. And the speed is known because we're talking about the speed of light, so that's constant. We want to calculate the distance, and the time is something that we have measured. Now the difference here is that we've actually measured the round trip. So we want half of that. We only want the distance from the scanner to the surface, and we don't want to add the other portion on the way back, because that would be twice the time or twice the distance. So when we rearrange this equation, the distance is equal to the speed times the time, but we have to divide by 2 because of the round trip. And it's a relatively simple sort of concept to get around. So this would be the basic time of flight scanner. This is what it would be doing: timing the pulse, and then just running it through a simple equation. At the very basic level, this is what it would be doing. However, there are other things that you can do with pulse-based, and I'll talk about that very briefly later on. So now we're going to move into phase-based or phase comparison, or even phase shift. So again, I've got a little graphic here, and I'm going to run through a few graphics here. This is not as simple to understand as time of flight, but we'll go through some of the basic concepts here. In this case, the scanner is not emitting a small pulse. What it's going to do is emit a constant wave, okay? And I'll back up here. So we've got a constant wave. So we're going to go forward. We've got a constant wave here that's being emitted. And that's going to, let me hit play here, that's going to hit a surface, and eventually it's going to bounce back. If the unit here sends out the signal starting at the top crest of a wave, let's just say that this is where it starts, when it hits the surface and gets reflected and comes back, it may not end up at the same spot. In fact, typically you're going to get some kind of a shift. And so if you measure from the crest of one wave to the crest of the other, you'll get this particular shift here. So the phase shift, okay, here it's theta, can be used to calculate time in this equation here. So the time is the phase shift over 2 pi f, which is the frequency. So, and then you can plug that back into another equation and calculate the distance. But there's a problem when you have just one wave, such as this that I've shown in this graphic. And let's move on to the second one so I can explain. So here we have something that's called ambiguity. And what I'm going to do here is I'll play this graphic, but let's assume that this is the wave that's going out, okay, so the yellow one here, and I've got the scanner, and I'm going to move the scanner to different positions, okay, and then what I have is I have the return wave here, okay, that's being reflected back. So when I do this, what you'll see is that I can move the scanner into positions which can coincide with the return wave, and there's many places that I can do this along the wave. So this is what's often referred to as ambiguity. We don't know what the shift is at any of those points. And so with respect to the scanner, if I move to this point, I've got no shift. So it would appear that there's no measurement, there's no difference in distance. Even though I've moved the scanner to another position, same thing here. There's no difference between the crests of the waves. So ambiguity is a problem. There's a way to resolve this, and so for that I need to go to the next slide here. Okay, so if I were to send out just one wave, I'm limited by that one particular wave, and so ambiguity can be resolved by using multiple continuous waves. And so in this graphic that I'll play here, what I've done is, let's just, it doesn't matter if these are all the waves that are either being emitted or coming back, okay? What's important to understand is that when you have a combination of waves like this, if you were to assume that these were all the waves that were coming back, if I were to cut these waves at any particular point along the path here, what you'll notice is that they make for a very unique combination. And so let's just run through this, and hopefully this will play for me properly. So at this particular position here, you'll see that I'm on the downside of the big wave and at the bottom end of the other two waves. Over here, you'll see at the crest of one, I'm on the upswing of the big one and on the upswing of the middle one. And here's one, I'm going to pause this for a second. So here's an interesting one. I'm on the down part of the big wave, but on the middle, I'm going down, and at the very bottom here of the little waves, the small waves, I'm at the very, very bottom. Okay, so this is somewhat similar to this over here for the middle wave and the bottom. So if we move that, if we continue to move that over to a similar spot, so I'm at the bottom of the wave, and I'm on the downside here, but you'll see that the large wave, okay, I'm on the upside. So it's unique. It's not the same as being here or at any other place along this combination of waves across this distance. When you combine multiple waves together, they form a unique wave or a unique combination of waves, and the scanner is typically set for or built around a specific distance. So if you were going to be measuring to 120 meters or 150 meters or whatever that might be, you would design the scanner so that the waves that are in that range coincide so that you don't get ambiguity. You can measure consistently within that range without any particular confusion. Let's continue on here. So when we're comparing time of flight and phase shift, there are some characteristics here that I would say are traditional. And so you see the word traditional come up here a lot. And I would say that, maybe 10 or more years ago, this may have been more true, but these things are starting to merge together. Things like speed, accuracy, those types of things are being improved on for both the time of flight and phase shift scanners. But let's go through them. Time of flight is typically better for long distances. That's generally still true. When we talk about aerial, Lidar, and mapping, those are typically time of flight instruments. And you can create a larger pulse, you can you can blast that pulse at the ground or whatever it might be, and then look for return signals. Traditionally, the scanning rates were a little slower than phase-based. Phase-based is typically faster, and time of flight is typically slower. And originally, time of flight would be somewhat more expensive. And again, this has probably changed. I would say they are in the same ballpark. But if you think about the components that you need to time light and to analyze the light, it's somewhat expensive, and so there may be a cost associated with that. One of the benefits, though, of time of flight, which is not really possible with, or certainly not to the same extent as phase shift, is that you can do different types of waveform analysis. So when you send a pulse out to a particular object, you may end up with 2 or 3 returns. And so as an example, the laser may hit part of a tree or a leaf, and then part of it might hit a sign, and then part of it might hit a building behind it. And so when all that comes back to the receiver, you end up with a number of small little blips or little pulses, little peaks that you would get on a signal. And so there's different types of analysis that can be done, filtering and that sort of thing. Now, phase shift is generally better for shorter distances, and some of the most accurate scanners in the world today are phase shift. So the Surphaser, which is a highly accurate instrument, is a phase-based instrument. Traditionally, phase-based scanners are faster, and I think that this is still true today. The capture rates or the scanning rates are very high, millions of points per second. Traditionally, these have been somewhat less expensive, but of course this depends on the type of technology that's in there. And they're also somewhat higher accuracy, and so you can build these phase-based instruments to get down to very fine accuracies and precisions. Although, and this is just probably been my own experience, they are somewhat slightly prone to more noise and different types of effects that you get by using a phase-based instrument, and I may discuss that a little bit more later. Let's move into the laser scanner and take a look at some of the components here. So there's really 3 basic components, or 3 things that are happening while scanning. And this is very similar to the total station. In fact, it is a total station, except for the fact that it automatically scans. And so the first component here is the range, is the distance range unit. In a total station, this would be called the EDM, the electronic distance measurement unit. And really what this is what we just talked about, which is the time of flight, or the phase-based portion of this, the Lidar portion of it, where it emits a laser and then calculates the distance. But as this mirror rotates around the unit here vertically, you're moving the laser vertically around in a 360. You need to be able to capture that somehow. So there is a component on the inside which measure the angles here, and as well as the horizontal angle. We know that the units spin around horizontally, so we have the laser moving vertically, and then we move the whole unit horizontally, so we can sweep a full 360 in the horizontal, and then in the vertical, depending on the type of scanner, you can sweep 300 degrees there, or something on that range. But of course, the scanner can't see directly below itself because it's housed in this particular unit. Now, when it comes to these angles here, well, how do we measure the angles? Well, the angles are typically measured by things called encoders. And these angular encoders are often little rings like this, and they can be optical. There's different types used for different applications. But if you were to etch or scribe, just like on this one here, a whole number of different markings here, okay, just like here, and you were to take a sensor, so for example, I took a cross section at any one point here, you'd see that you have a certain combination of white, dark, white, 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 dark, white, white. And so depending on how fine this is, this angular encoder, as this rotates around and you read any of these strips here, you have a very unique position. And if you know where your, let's say where your home position is, or for example here is a different one. This is called an incremental encoder, and you'll see that you have a lot of these notches and they're kind of offset a little bit, so you can tell the increments. You can tell how it's moving incrementally. But here you can see there's one notch right here, which probably tells you, well, that's like a home position. Okay, so these may be able to tell you absolute relative to a position, and these will be able to tell like increment, that you move 3 or 4 steps ahead or backwards or whatever that might be. But the point here is that there's something called an encoder. It measures the angle of where the mirror is pointing, and that's important to give you both the vertical and horizontal angle. Okay, 2 things to understand is that just like a total station, a laser scanner also collects data in a polar coordinate system. And so what we have is, if we consider that the mirror was right at the 0, 0, 0 point here of a coordinate system, we are calculating the distance, and that can be seen like the radius of a circle. And what we have is the angle from the mirror, so that gives us a vertical angle, and then we have the horizontal angle. Okay, so that gives us an angle away from some reference horizontal axis. So by knowing these 3 particular components, we can define a point in space. Now, fortunately, we convert that over to Cartesian coordinates, or the software will convert that over to Cartesian coordinates for us, which is just an XYZ coordinate system, because it's a lot easier for people to understand. If you gave people 27.6 degrees vertical and 36 degrees horizontal, and the radius is going to be 37 meters, it's not all that simple to understand what that means in your head. So understanding XYZ components is easy to sort of rebuild in CAD programs and things like that, and some people can imagine it a little bit easier. So we use the Cartesian coordinate system, but understand that all the measurements are originally captured in a polar coordinate system. So 2 concepts that I think are important to cover are resolution and quality. And these are very common on almost every single scanner that I've seen. And let's talk about resolution. So when we talk about resolution, we're talking about how fine of a scan that we're getting. You can think about it as the resolution of a scan. Now typically, and there are different ways to define this, but most people define it as a certain point spacing at a specified distance. So if you were to go at a 10-meter distance, you would find that the distance between the points that the laser scanner captures will be so many millimeters, something like this. Resolution is dependent on where the object is. So you could set it for a point spacing at 10 meters or something like that. And so an object that was somewhere at about 10 meters, would have a point spacing of X, whatever that might be. But of course, as you move an object closer to the laser scanner, these lines, okay, between one sweep of the laser and the next, they converge, okay, or meet right at the center of the mirror, because that's where the laser is being emitted. And as a result, objects which are closer will have a tighter point spacing. They'll have a higher resolution than objects which are farther or further away. And so resolution is an important feature of any scanner, especially when you're recording evidence, or you're capturing something that's very far away, you want to increase, or if you're trying to use targets. All of these things are dependent on the resolution. Now, quality is a little bit different, and quality, a word that can be used synonymously with quality, is sampling. And sampling really just comes down to taking a number of measurements for the same thing. Now, because light travels so fast, what we can do is take multiple measurements here. So if we're taking originally 5, 10, 15, many scanners have different settings where the mirror will move a little bit slower to give the laser more time to come back, and you can take multiple measurements. Now, in something like a total station, I did some research. I have a Sukiya total station, and when I take a single reflectorless shot with the total station, I'm not just taking 5 or 10 or 20. I'm actually taking thousands of measurements of the same thing. And with those measurements, I get an average and I get a standard deviation. Now, one of the benefits of using a total station is that it will tell you if you get an error or if there's a problem with the error right there on the spot. Of course, with the laser scanner, because it's spinning and it's autonomous, it doesn't give you that benefit or that kind of feedback. It may just collect noise. So if somebody just walks in front of the scanner or a car drives by, unfortunately, you've collected that data. It's something you have to clean up afterwards. But the point here is that with greater quality, the scanner does not move as fast. It takes a little bit longer, and that's because the laser needs more time to collect data for any one single point. But of course, the benefit is that with higher quality, the points are more accurate to the actual location of a surface or an object or whatever it might be. I want to talk about a couple of other things I think which are important points when it comes to understanding the laser. And of course, in order to obtain a measurement from the laser, we need some kind of reflection, right? So the laser hits an object, the light gets somewhat scattered and comes back to the laser scanner into the receiver, and the receiver is going to measure how much of the light comes back. And from that measurement, of course, it can calculate the distance. So understanding reflection and refraction can be helpful. And so for a perfect mirror, there are a couple of things with the law of reflection that's really simple, and that is that the incident ray, which is coming in here, is equal to, so this angle is equal to the reflected ray. Okay, so it's very simple. If you had a perfect mirror, incident ray comes in and then it gets reflected at the same angle. Now, in some cases with the laser scanner, we don't always need a perfect mirror. You can get this effect off of different things, like for example, windows or tinted windows and things like that, especially if you are on an oblique angle. If you're on a very, very shallow angle, glass will act very much like a mirror because most of the light that hits it is going to be reflected away, and so only the portion that gets mirrored, let's say, that kind of reflects away, comes back to the scanner. So other components here is that the incident ray and the reflected ray fall on the same plane, and there is a normal ray which is perpendicular to the surface. All three of these rays are they lie in the same plane. Okay. Let's move on to refraction. I think this is probably the more interesting of the two. So refraction is the change in direction of light when it passes through two different mediums. And so I've established a graphic here. I've got air, let's say on the outside, and let's say that this is a tank of water without the container. Somehow I've managed to keep this into a nice rectangular box of water. And on the outside here I have the index of refraction for air. This is N1, and this is the index of refraction of water. This is N2. Now, the index of refraction is a measure of the speed of light to the velocity of light in air. And so in the case of air, it would be very close to 1. Okay, so the speed of light, I think at the beginning I said there was about a 0.03% difference in the speed, so you would end up having, 1.00 something. It would be very close to 1 for the speed of light in air. And then for water, I think we said it was about 25% different, so you'd have a higher number for water. So N would be 1 point something, much greater. So what happens here is that when we have an incident ray, so we're going to call this the incident ray, and it comes at this particular angle, and we're going to call the angle to the normal. Again, we're establishing a perpendicular to this surface here. Let's say there's a perfectly flat surface. We have the incident angle. Now, if we didn't get any refraction, we would expect the light to just continue on its merry way straight through, and everything would be nice and simple. But that isn't, in fact, what happens. So once light moves from air, okay, into a denser medium like water, what actually happens is we have refraction. So the angle here, okay, so theta r and theta I, so the incident and reflected angle, are not identical. Okay, they change slightly. And what's interesting is that when you move from less dense to greater density, the refracted ray moves towards the normal. Okay, so it bends this way, it bends down towards the normal. Now, if we continue this on, create another normal here, because this ray is going through the water, it wants to come back out into the air, we have something like this now. Okay, so we have the light coming down this way, it hits the water air surface, it's moving into something which is less dense now. So dense water into less dense air. Now the ray bends away from the normal. So you see it went back this way here. So now we have the emergent angle. So you can see that the path of the incident ray, okay, or the original ray as it comes through, gets bent through here, and there's a slight shift at the bottom. So this is really interesting to understand, especially when we're talking about the effects that we get through things like glass or scanning through glass. So let's take just a quick look at this. I love this graphic here. We've got a laser that's coming in, and we see we've got this sort of a semicircle prism here, glass prism, and the laser light comes in, hits this point here, and you can see part of it is actually reflected away, and part of it comes in. And there's a shift. If you were to continue on this path, it would go straight this way, but of course it gets refracted, and you can see that it moves towards the normal. Okay, so it moves towards the normal. Now, because the surface here is perpendicular, it actually goes straight through it. So it didn't refract back out. It didn't come out at an angle. And I think that's probably why they're using this semicircle. But you can definitely see that there's a refraction at this particular point here. Now, there's some other technical things here with respect to the ratio of the index of refraction for air and for glass. Nonetheless, what you have to understand, or what the most important thing here, is that when the light comes in, it's bent either towards or away the normal, depending on the density of the material. So it shifts its position, it shifts its direction. So this is a little experiment that I did, and what I want to go on to now is just to look at some of the effects of scanning. So this is one where I've scanned through glass. So you'll see there's actually two doors here. This is one scan with the door which is closed. This is one scan with the door that's open. And I've registered the two together, so I've overlaid the two. So in one scan, the door is closed and it has glass here, and I've scanned the wall back here through the glass. And what I'm looking for to see is, if I have the door open and I scan the wall, and then I have the door closed and I scan the wall through the glass, what is the effect of the glass? What is it going to do to my points? So let's play this here, and I'll walk you through what it's showing. You can see this is the scan of the door. The door is highlighted. Okay, here with the glass. This is with the door open. So I've scanned the wall with the door open. And I may flip through these. Now you look at the registration between the two, or the alignment between the two. So this one is the open door. And now I'm going to switch back to the closed door. You see that the points here on the wall, which is common to the two scans, is very, very similar. So what's different is the wall at the back, right? You see the wall at the very back here. So now what I'm doing is I'm showing the open door, or excuse me, I'm showing the scan of through the glass. You'll see that I have a bunch of points at the back. Okay, so I have some offset. So there's some difference between the open door and the closed door. I'm actually going to go back here to show this to you again. So let me back up here. So I've got, okay, this is the scan of the through the glass door, because I can see the door is highlighted here, and I'm going to move back here. So if we look at this here, the highlighted points are sitting farther away. They're just slightly farther than the scan with the door that's open. And you'll see that it's not a lot, which is kind of surprising. Now there are other things that happen through glass, including noise, and this is anecdotal for me, but depending on the angle in which you scan and things like that, there are other things which can happen. But what I want you to see here is that there is a slight shift in the points when we go through glass versus when we don't here at the front, and you can see that they're not aligned the same as the points that are at the front here. And I've run this experiment a couple of times in different situations, and I've had the same result each time. Okay, let's go on. So let's talk about wet surfaces. This comes up often as a question, and it's really dependent on the type of wavelength that we're using. And again, I'll go back to the 1550 nanometer wavelength because it is one of the most common wavelengths. And this is an image. You can see there's a lot of water and wet surfaces here. There's wet vegetation and all kinds of things. And so this is the photo that was captured, and this is the data that was captured. And what you'll see here is that in areas where we have shallow water, so very little water, or maybe just the surface is wet and muddy, we collect data pretty well. Now, in areas where we have pooled water or puddled water, well, the laser doesn't penetrate. And as we know, 1550, as we looked at before, it gets absorbed by water and by moisture, so as a result, we're not going to get deep penetration. The other thing that we just learned, or that we just talked about, was refraction. And so when we start having puddled water, even if we were able to scan through there, we have to take into consideration what the index of refraction is doing. So if we're trying to do something that is highly, highly precise, there may be some effect there. And I can't say that I've done enough to actually quantify this in any one scenario. But safe to say that it's probably a good idea to really consider your data if you're going to be using anything that's through glass or that goes through water. Okay, let's talk about edge effects. Whenever we're scanning objects, of course there's always objects that have corners or curved surfaces or whatever that might be. And of course, the beam that comes out of the laser has some thickness to it. So whenever it hits an object that at a perpendicular position, that's about the best you're going to get. That's when you're going to get a full return of the signal, and it gets right back into the scanner. Now, when we start getting to the edge of an object, and it could be something with a sharp corner, it could be something that's slightly rounded, we start getting into a little bit of problems, because part of this beam is going to hit the edge of this particular sphere, and part of it's going to hit something behind it. And so as a result, we may get multiple returns, or we may get multiple things coming back to the scanner. And this is often, people will call this as noise, some people call this as edge effects, but it often gives us something like this. So in this particular case, this is very pronounced when you have things like chain link fence, or when you have, forgot what they're called, but like stanchions or posts on a railing and that sort of thing. You will get a lot of this noise, and that's really what's happening, is that the beam is hitting the edge there, is hitting the edge, and it's hitting some different things. And one key feature here is that you'll note that the noise, or these effects, happen in the direction of the laser. So in this particular set of noise here, I know that the laser was on the opposite side of the noise, so it's to the left here. The laser would have been mounted on the left, and the laser scanner would have been to the left, but the laser itself would have been traveling to the right. So let's discuss a little bit regarding accuracy and error, and I see that we're getting on here on time, so we're going to wrap it up pretty quick. There are three components to the measurements of the scanners that we discussed before. There was the range, there's the vertical angle, and that there's the horizontal angle. And so we have to be able to combine these three things and consider these three things when we're talking about errors and accuracy. I'm just going to slide this animation, this graphic here. So if we're talking about the range error, so just down here where the scanner's mirror would be, it would shoot a beam out, and let's say it would hit a point somewhere over here. Well, there could be a plus or minus error range on this thing. So we start, I'm just moving this little point here forward and back, something like this. So that's one component of the error. The other component of the error is the mirror, is the vertical angle on the mirror. So now that point here that's been measured may be pushed up and down. So if I move this way, okay, we could have a problem with the point being positioned incorrectly, both up and down in the vertical, but also in the horizontal here. So there's a horizontal angle and a vertical angle. So when you think about all the positions where that point could exist, so basically looking at the away and closer to the scanner, and then sort of up and down vertically from that position, and then side to side like that, you end up with a type of error ellipse, or you end up with an area which defines all the possible locations where that a point could be. So we could call this like our uncertainty. And so that point is can be calculated through testing. It can be calculated through knowing the errors in the individual components. So understand that there is a range here of error, and it ends up being a type of ellipsoid or egg-shaped object that defines all the different spaces. Now, what I'm going to do is I'm going to convert from polar to Cartesian because it's just easier to understand. But let's say that inside that ellipse that we just had, that P1 is where I know the point to be. So that is actually where it is. And I had another instrument, I checked it, and I know that P1 is actually located at X1, Y1, and Z1 in this particular position. But let's say now that the scanner is telling me that it's actually over here at P2. So now I have slightly different coordinates for this. I've got X2, Y2, and Z2. So there's a difference between these two positions. And I can calculate the total error. Okay, I can calculate the distance between this point and this point by looking at the 3D distance equation here. So if I have point P1 with X1, Y1, Z1, and I have point P2 with X2, Y2, Z2, the error is equivalent to the distance between those 2 points. And this is a formula for it. So what you're going to do is you're going to subtract the x's, subtract the y's, and subtract the z's. And it doesn't matter in what order that you do it in, so long as it is consistent. You're going to square their differences, add everything together, and then take the square root. So here I've got just a very simple example, and this is important. You can probably expect that there will be some questions on this if we have an exam, but if we take a couple of points, 2 minus 4, 8, and P2, negative 6, 2, negative 3. When we punch these into the equation, be careful with negative numbers when you're subtracting negative numbers as they become positive. Square the results, add them together, take the square root, and you end up with your total error. And in this case, again, these are just sort of easy numbers to work with, but normally these would be numbers with a considerable amount of decimal places after them, and we would hope that the actual location and the location provided by the scanner would be fairly close. But this is one way to look at the errors and how to calculate them. So I'm going to finish off on that note. Hit just over an hour here, and because this is pre-recorded, I may not be available on the other dates. However, if you're listening to this on the first broadcast on October 26th, feel free to ask any questions. Also, I would like to add that this is, again, sort of a very basic introduction to some of this stuff, and I know that there's some really good information out there that the manufacturers have. Always looking for better information and how to improve these things for our certification course, and so any feedback or any suggestions, any information you have is welcome. So thank you, everyone, and we'll move into questions now.